So, Michał Stęchły. How did I do in pronouncing? Not,
Close
not,
enough.
not bad for okay. All right. And introduction to quantum resource estimation. We're all looking forward to it. Do you want to introduce yourself, or should I briefly say that you work as a senior quantum software engineer at PsiQuantum, the lead developer at Bartiq? And should I say anything else, or just let you go on?
Let me go on. Thank you
All
very
right.
much.
Okay, good. Here we
So
go. The floor
let's
is yours.
share my screen. Okay. Can you see my screen?
Yes.
Amazing. Hello, everyone. Hello, everyone. Thank you very much, Barry, for inviting me. As you said, my name is Michał Stęchły. I work at PsiQuantum. And before I get into the slides, there are two important things. So one is three important things. One is it's at 10 p.m. here. So if I'm sometimes have some lapses of tongue, then I'm sorry for that. Second is please, if you have any questions, I will be please type them in the chat, and I will be making pause every couple of slides to make sure I answer all the questions and we can have some discussion. The third thing is, in case my connection sometimes breaks, so in case that happens, please just wait 30 seconds and I should be back. So no worry about that.
We'll just make something up in your stead.
Yeah, thank you. So the plan for today is, first I will talk about some key differences between NISQ and FTQC in terms of algorithms and application development. Then I will talk about some main challenges in development of applications and algorithms for FTQC, and then get into quantum resource estimations, overview of like different flavors of that, etc. So first about me, I'm Michał. I work as a quantum software engineer at PsiQuantum, where I work on resource estimation software mostly. Previously, I was also quantum software engineer at Zapata. I don't come from academia. I've been working as a software developer, before getting into quantum, but I also have finished bachelor in physics, master in automation control and robotics, did some machine learning. So, I like to basically know a lot about many different things. And I also involved in many community initiatives, like, for example, QOSF mentorship program, or Unitary Fund, or IEEE Quantum Week Conference, and many others. So PsiQuantum, as I mentioned, I work for PsiQuantum. And for those who don't know, our mission is to build the first useful quantum computer. We are based in Palo Alto, California. The company is, I would say, pretty old as for quantum startup, as we were founded in 2017. The computer we are building is based on integrated photonics. So this is the approach that's quite different from most other hardware vendors. And we are from the beginning very focused on working on building fault-tolerant quantum computer and making sure that it's scalable. And what I think is important for this particular meeting is that we plan to build our first device in US in Chicago. So glad to be in this particular meetup. If you have any questions about our hardware, feel free to ask me afterwards, but I'm probably not the most qualified person to answer them, as I work on the applications team. So the role of my team is to find the most useful applications for the computer we are building, and to make those programs that we'll be running as resource efficient as possible. So let's take a look at the comparison between NISQ and FTQC algorithms programs. So the thing with the NISQ, let's say variational quantum algorithms, right, is that they don't require a lot of operations and they don't require a lot of physical qubits, which is good, right? Because this is the reality of these devices. But the problem with them is that in order to, for example, get a single energy estimate, you need to run the same circuit many, many times to get good statistical results. And then this is only to get like one energy estimation, for example. So in order to actually optimize the parameters of your ansatz, you probably need to run it, many, many times more, each a bunch of times for each optimization step. And this is, I would say, somewhat contrasting with the scale of what we are trying to do with fault-tolerant devices, as here we are talking about orders of magnitude more operations, like orders of magnitudes bigger devices in terms of qubits, though at least some good side of that is that you usually only need to run the particular program once or a couple of times to get the results and not millions or billions of times. So an example of a project that I would say was a very good example to show this difference was trying to get the energy estimate of H2O molecule, which definitely is a toy problem. So it doesn't have much like practical application. But even for this small example, you can see what are some issues with the NISQ paradigm. So this was here are a bunch of assumptions going into this particular project. This was the work that was done by some people at Zapata in around like 2020, and we were basically comparing the resources needed to get relevant calculate the ground state energies for set of problems, including even molecules like water, down to chemical accuracy. And the problem with that approach was that even though you needed only 80 qubits and running one circuit was taking around 40 microseconds, given some pretty optimistic, let's say, assumptions, then in order to measure, to get enough measurements to be able to estimate the energy with the good enough accuracy, you had to run it about 2 billion times, which was taking like 22 hours. And then
Annoying.
you had to, afterwards, this is just for one energy evaluation, and in variational algorithms, right, you need to do a lot of those evaluations one after another in order to optimize your parameters. And being, again, slightly optimistic, if you just run it 100 times, like for 100 iterations, well, this doesn't give you much of the guarantee that you will succeed. But it's already takes about like 3 months to get the result. And I would say that like why I'm even talking about this, right? This is not to kind of say that, hey, NISQ is useless and FTQC is kind of the only sensible thing to do. But this is rather to first show that there are, once you start kind of digging into this, there are like certain limitations of NISQ devices. And I honestly would be happy if someone kind of proves me wrong, but I haven't heard about people overcoming those limitations yet. But the other thing is that because a lot of the algorithms for NISQ devices are variational, they're heuristic, it's really hard to do any resource estimates because you can kind of prove that some application will not really work because you have to run the algorithm for, I don't know, like a couple of months, couple of years. But it's very hard to prove that something will work because you never know how many iterations you have to run. So that's why I would say for the variational algorithm, there's not much work on resource estimation because it's extremely hard problem and really hard to solve it without, it's somewhat like easier to actually run those algorithms and see how it goes rather than try to figure out how to resource estimate it in the level of detail that we can do for fault-tolerant devices. So when we compare the world of variational quantum algorithms and the world of like fault-tolerant algorithms and applications, then basically everything is different. Like I used to work on variational algorithms, and when I started working on fault-tolerant ones, it turns out that the applications we are looking at are very different. The algorithms are just different classes of algorithms. When we're performing compilation, this is also very much, two different kind of types of compilation, and we kind of minimize different things. And like the whole software stack is really very much different. So today I will focus more on the algorithms and compilation. When we are looking at fault-tolerant devices, I would say most widely used algorithm that people look at is QPE, quantum phase estimation. And on a very high level, it looks something like this, right? It has a bunch of kind of qubits where we encode the phase. It has some other qubits where we encode a particular state, and it takes as an input some unitary U, right, which kind of defines our the Hamiltonian, right, that describes our problem. And I would say that we'll now focus on how do we do this encoding. A way of constructing this matrix U is to do something called block encoding. And here we see a circuit which creates block encoding for a technique called double factorization. And I don't want to go into details about those algorithms. This is just like show how they kind of look like what's their high level structure. And we can see that there is some symmetry in this picture. Right, actually, we can show there are like three distinct parts, which is select, prepare, and reflect. Each of them is kind of computed and uncomputed. And if we just look at one of these boxes, so we'll look at this one here. It's sometimes called QROM or data lookup. Sorry, before we go there, if we look at this circuit, actually all the purple ones are arithmetic subroutines, right? So they are doing something classical, and in this case, they're actually just doing mostly data loading. So if we look at the QROM, it looks something like this, depending on what kind of classical data we are trying to load into the memory of our quantum computer. We'll have those question marks either black or white. But this is, again, very different from many of the, kind of variational circuits, as we see a lot of those gates are multi-control gates, which are ubiquitous in kind of fault-tolerant algorithms. So when we look at a circuit from the perspective of variational algorithms, we can say that all the 2-qubit or multi-qubit gates are very expensive, right? All the 1-qubit gates are basically cheap, and the measurements are also quite expensive. So when we're performing compilation of such circuits, this is what we're paying attention to, like 2-qubit gates. On the other hand, when we look at the fault-tolerant algorithms, we use very different metrics, right? The expensive ones are not multi-qubit gates. The expensive ones are T-gates or rotations, or in general, like any non-Clifford gates. Measurements are relatively cheap, and all the Clifford gates, so your Hadamard S gates, C-naughts, are kind of basically basically free if you compare their cost with the cost of the T-gates. This picture is actually changing if we look at the results that the Craig Gidney has published, I don't know, earlier this year or last year, the work on cultivation. It turns out that, under certain conditions, we can limit the cost of T-gates so that we suddenly need to start worrying about the Clifford gates. But in general, if we compare these two pictures, they are very different. And a T-gate is rotation by, I think, the pi8 or pi4. I always forget. So this is RZ with pi4. I'm frozen. Do you hear me? Okay. I see in the chat someone said I'm frozen. Do you hear me well or?
I hear you. I don't know if everyone else can.
Okay, great.
I can hear you fine.
Awesome. Thank you. So, oh yeah, T is z rotation by pi4. Awesome. So, okay, so how do we, even perform in the compilation for fault-tolerant algorithms? There is a lot of steps in this pipeline, but one of ways to translate those logical circuits to more operations that are actually executable on a quantum device is through a procedure called lattice surgery. And in order to get there, we can, and to get into the details of this, I highly recommend the paper Game of Surface Codes by Daniel Litinsky. It's absolutely phenomenal paper. But what we have here what the gates are. So what we need to do is we first need to translate this kind of regular circuit into the circuit that's constructed from Pauli product rotations or Pauli product measurements, so PPRs and PPMs. So basically, it's just a particular formalism for expressing gates rotations in this layered format. And this is useful because then it allows us to kind of map those gates better into some kind of the architecture of the computer, right? So if we have a grid of qubits and each square on this grid is kind of, let's say maybe not qubit, is some unit of computation, right? We can encode it in such a way that, or maybe, no, sorry. Okay, let's say each square is a qubit, right? We can take and use more of those kind of qubits to encode a particular state. And here we have, 5 different states. And when we want to perform operations, we can take those circuits written in the PPR and PPMs and translate them into particular lattice surgery operations, right? So for example, here, if we want to perform this particular operations like X on the first one, Y on the third one, and Z on the fourth one, we just do kind of something like that. Again, I don't want to go into details. I just want to show some of the kind of levels of complexity of kind of doing compilation for fault-tolerant computers. So you can translate each of those steps into certain lattice surgery operations. And if you look under the hood, actually, you can translate each of those square into kind of physical qubits, right? Each of the square corresponds to, let's say, d squared physical qubits, where d is the code distance. So as you can see, we are kind of going through several layers of abstraction. And the problem is that at each of those layers, there are certain optimizations that can be made. There are different strategies there, because optimizing kind of, things that look like this are very different from optimizing circuits that look like this, right? You need different software and different methods to do that. And actually, if you don't take into account some of those steps, then you might be getting kind of less realistic results. So if you your resource estimates might be off. So I would say last comparison between kind of NISQ and FTQC that I will make is that if we think about NISQ devices, right? Maybe let's put it this way. Like sometimes when people think about going from NISQ to FTQC, they think, that it's like going through a simple C8086 microprocessor to like Intel i7. But actually, there's just so much more complexity in the fault-tolerant stack that it's much more than going from a single, chip to an actually supercomputer. And that's why, we just that's like one of the reasons also why doing proper resource estimation is so involved. So this was a bit about how the software stack looks like for FTQC versus NISQ. Now I will go into some of the current challenges in the development of algorithms and applications. But before I do, I don't see any questions in the chat, but I think this is the right question if you have any questions the right time to ask any questions if you have them for what I just said. If no, then we'll just go.
I do have a
Sure, please go.
You still there, Barry?
Okay. Oh, it was Barry or me? Okay, can you guys hear me?
Yes,
I can hear you, but Barry fell off.
Okay, Barry.
I can hear.
Okay. So, oh,
okay.
Barry. Okay. Oh, Barry's back?
Okay, you can hear me. All right.
Yes.
Let's go back. Let's go back to the slides that say free, cheap, and expensive.
Yeah.
Right. NISQ, I understand. Go to the next slide.
Yeah.
Why? What is it about FTQC that makes these colors different? These
Okay.
ratings are cheap and free.
So I would say that the reason that the Clifford gates can be free is because you can apply some very, very smart accounting to that basically reduces their cost a lot. So there are certain protocols that allow you to, let's say, like perform some transformations. So you can push all the red boxes to the right and all the green boxes to the left, and then basically you can collapse a lot of the green boxes with each other because if you have you can transform a lot of them to other kind of smaller amount of the green boxes. I think the bigger part of the question is why the red ones are so expensive, and this is because creating T-gates requires a process called magic state distillation. And this is because you kind of, in the fault-tolerant architecture, you cannot produce those T-gates with infinite precision. And you have to kind of approximate them. And in order to do that with kind of enough fidelity, you need to prepare a lot of those states then kind of distill them into like purer states and distill them further in purer states, which is a process that just like takes a lot of resources. So the way a lot of the fault-tolerant architectures are set up is that you have a part of your quantum computer which is used for, let's say, performing calculations, and then you have like a big other part of quantum computer which is just used to make more and more kind of pure versions of those T gates. And kind of that's the kind of part of the reason why this is they are just like so much more expensive. And as someone mentioned, this is somewhat similar to ZX calculus, and yes, it is. I'm not sure if there's like one-to-one mapping between the lattice surgery and ZX calculus, but I think there are like definitely a lot of at least a lot of parallels. So, for example, rotations are another example of very, very expensive gates, because rotations are, if you want to rotate by like an arbitrary angle, you need to do that up to certain precision. And because the operations we have are digital, you need to kind of approximate that. And you do the approximation with a series of usually H, S, and T gates. So performing any rotation just takes a lot of T gates, and T gates are expensive. Does it make sense?
Oh, that's great. Thank you.
Okay.
So I have a question if nobody else is ahead of me. Generally,
I stopped hearing you.
I stopped hearing Dave also.
oh, really?
Yeah, we hear you very weakly.
Yeah.
Yeah, let me see if I can adjust it or something. How are we doing now?
Stay close to the mic and you'll be fine.
It's good.
Okay.
Back.
All right. So in general, when you have different types of technology in this field, what happens is that you wind up with different gates cost different amounts of resources. And I see that you've broken that down for two separate cases here. Now, two things. One is rotations. Are you including polarization as your basic method of encoding the quantum state? That's I seem to recall that's a relatively cheap operation. You can get half-wave plates and so on. And the other question is, what exactly are you using as your encoding methodology?
So I would say that the problem with, okay, I will try to answer your question indirectly, and once I'm done, let's see if that actually answers it. So the problem is that if you are using fault-tolerant, you want to use fault-tolerant architecture, you want to be sure that you want to have some arbitrary succeed rate, right? Like, so you want to make sure that the operation that you actually made is 99, comma like 7 9s correct or whatever. And therefore, you cannot rely on physical processes. So if your qubits can, in some smart way perform rotation, you could like do rotation on a physical qubit in some smart way, then it will have some limited precision due to, well, just, the fact of the kind of physical processes, noise, etc., etc. And therefore, in order to make sure that that kind of abstract logical rotation that you wanted to perform is done correctly, you need many layers of error correction and some like redundancies. And therefore, I would say that most of the time, when it comes to this class of algorithms, you have you operate on a logical layer, right? So this is basically the kind of ideal operations that you want to perform. And you don't really bother at all how to map them to the hardware, because there is just like a other huge software stack that like allows you to do that. And if particular hardware modality, I know, supports some particular operations in a better way, then this might give you some savings on some other levels of the stack, right? But you won't see that on the logical level. Does this answer your question?
I'm not entirely sure. What I'm thinking is two things. You can purchase commercial half-wave, quarter-wave plates and so on that will perform rotations. You can also purchase various chemical cells that will perform rotations. These do have a certain dispersion.
Can you come closer to the mic? I lost you.
I'm sorry. How's that? Is that better?
Now good. Now good.
Okay. So you can purchase off the shelf commercial stuff that will do rotations optically in various modalities. They typically have dispersion of frequency. That's not really an issue if you're using lasers that are monochromatic. Also,
Okay. So
you can get these things from Meadowlark that are electrically programmable liquid crystal optical rotators that can be programmed with a feedback system.
okay, so I would say this, like let's look at this picture here. These, like each square here is 25 qubits, right? And so 25 physical qubits. So these two patches, I mean, I probably am making some oversimplifications, but I think that's for our purposes should be good. So these two patches are like 50 qubits, and those 50 qubits kind of represent one logical qubit. So if you want to perform kind of a rotation on kind of one logical qubit, then you would need to perform a lot of operations on those like 50 qubits. Then if you want to do a 2-qubit gate, then that's, you know, even more involved, right? Because you need to connect those qubits with like some other qubits, and that involves like a lot of other extra physical qubits. And the problem is that you just need to orchestrate all that, and you need to make sure that it's error corrected, so that if any single of those operations, like rotation that you made, you know, fails, then like all the other stuff still works. And that's why I think the fact that you can have optical components that can perform rotation on, you know, like let's say one physical qubit, it just like doesn't scale well to like the logical level, right? Because just like the errors, if you try to do an algorithm on like 100 qubits and perform those on each of those qubits, like, and let it run for a billion kind of different operations, then I think the errors will just accumulate and totally devastate your results. And that's why you need like some extra levels of indirection.
I see. So it's yet another example of the error cascades that we see all over the place.
Yes. Though at the same time, take what I'm saying here with a grain of salt, because I'm not experimentalist and not even working on error correction. So my understanding here is, you know, I might be not understanding certain details or nuances, but I think like on the big picture, I think this is roughly what happens.
Thank you.
So let me move into the challenges that, you know, we face when it comes to developing algorithms and applications. So I really like this talk by my friend Yuval, where he talked basically, why quantum algorithms papers are so long, and what do we mean by so long? Well, here is a paper which describes double factorization algorithm that I showed on like some previous slide, and this particular paper has 73 pages, and well, that's a lot. This is a very, very hard paper to read, ingest, and decipher. I have only, understood small parts of it. And I would say that, one thing is understanding that paper, reading it, but then if you want to actually take an algorithm like double factorization and you want to perform, know how long it will take to run this algorithm. Like this is big part of those like 73 pages is just describing different boxes in this big algorithm, describe them in a more detailed way until at some point you can make some statement about, okay, this particular part, now that we have decomposed it enough, will take, I don't know, n t-gates, or will take n plus 2 rotations, or whatever the kind of expression for that would be. And then this is a screenshot of like some Mathematica notebooks that we have built in-house to actually get some of those QREs for this one particular paper, right? So there is a lot of very bespoke manual code that had to happen, and this is just to reproduce some of the numbers from this one paper. And this is problematic, right? Just like the scale and the complexity of these algorithms is a problem, and also the scale of complexity of the papers that describe them. So when we look at a particular project that tries to find a new application for a quantum computer or improve in some way upon existing applications, and this is not just for what we do at PsiQuantum, I would say this is quite true for other groups that work on similar problems. And usually the way it looks like is like this. And just keep in mind, like this slide was made, I mean, maybe not this particular, but like the numbers here are from roughly 2 years ago. And the 2 years ago, the numbers, oh, sorry, I messed up my slides. So first, I wanted to say that the second piece of data was the timelines of like when we will have fault-tolerant quantum computers, and these are just the numbers, the years I took from what these companies say, right? So IBM said they will have FTQC by 2029. IonQ, well, there's caveats on like how you want to interpret what algorithmic qubits mean, but it looks like 2028 is when they want to have roughly some early fault tolerance. And then we at PsiQuantum, we want to build our first computer in Australia by the end of 2027. And this is like 2.5 years from now. So that's not that far away in the future, right? And that's the perspective that we have internally as our team, that we really need to optimize those algorithms and build, find more applications, because there is not that much time to do that. And basically, if I could conjure an FTQC with a magic wand and it would just like magically happen in front of my house, how many practical problems, I mean practical meaning having some application in the real world, like some usefulness for certain people, would we be able to solve using what's available today in the public domain? Right? Like how many algorithms basically we have written down to the level of gates so that if someone gave me this computer, I could just load my program into its memory and run it. Like, do we have any guesses?
I'm going to
No.
guess few.
Few is a good guess, yes. So up to my kind of best knowledge is maybe one, and the one is Shor's algorithm, basically. Like some people have done really good job in the last couple of years of compiling the Shor's algorithm down to some actually somewhat like executable format. All the chemistry, materials, applications, there are still certain black boxes in those algorithms that people have not, let's say, like solved, at least not publicly, right? I mean, I don't know what different organizations have, internally, but I don't think there are any papers or pieces of software which specify some of those algorithms to the level of detail that is required to run them. Right. And as I mentioned, the part that I'm mostly spend most of my time is the part about useful quantum computers. Other people in the company are, more concerned about building the computer. And fortunately, if we look at different resource estimates for different algorithms, applications, like maybe applications is a better word here, we see that in the past we have seen like amazing improvement, right? Like this is like log scale. So over the years, there are some trend lines, and the resources needed to run these algorithms are, improving at a good pace. But at the same time, basically coming up with any single of these dots is a very, very long and complicated process that usually is, kind of one-off project that takes months. So as an example, and this is where, sorry, I got confused before. This is what I was saying, that this is a project, the timelines for a project, which are representative, not just like for this particular project, but for other projects that, other people in the field do. So how does working on a quantum application usually looks like? So usually we start from problem definition, right? And this is something that takes weeks. And this is, taking a real world problem and translating into the format that we can do something with, right? So either some equations, maybe defining some Hamiltonians, that depends on the kind of domain. And then there is another stage, which also usually takes weeks, maybe 2 to 3 months, which is selecting what algorithm is the best to solve the particular problem that we want to solve. Then you would like to actually build this algorithm in, some format. You can't just say, oh, I would just use double factorization and call it a day, right? You actually need to take all those kind of subroutines and boxes and instantiate them in one way or another. Sometimes this is using code. In some other cases, this is actually just doing a lot of math. And this is, I would say, like a very big part of the process, and it can take easily a couple of months. And then compilation. So once you have this algorithm written in terms of some subroutines, you want to take those subroutines and compile them down to, preferably some like logical circuits. And you want to make sure that, this compilation process is performed correctly. And only when you have this, you can get into the resource estimation, which is trying to answer the question, okay, now that I have this algorithm written in this particular format, how long it will take to actually run it on a quantum computer given certain assumptions. And when this is done, well, we kind of get back to the stage of constructing the algorithm, and we can do some optimization and just, basically get in the loop here. So that's how it looks like. And the problem with this picture is that getting the whole project done takes 6 to 9 months. And if we are a bit more pessimistic than the data that I took from public releases on a couple of slides ago, let's say we will have a working fault-tolerant quantum computer by 2030. So if we take a look at this optimistically and we say, okay, it will take 6 months to do this, then this means that from today to the end of 2030, we will be able to do 9 projects like this. So basically 2 projects a year, and there is half a year already from 2025. And that's not a lot of projects. And you finish one project, you take some learning, and then you start working on the next one, and you iterate like that. And basically, given those timelines, the speed at which these projects are done is just like too slow. This is not, it will be foolish to assume that with just like 9 iterations, we'll be able to really make very big strides in the terms of developing new applications for quantum computers. So, this whole process is very slow, very painful, and really I haven't heard from anyone working on this that anything else. It usually is really, really kind of, it's very meticulous process, basically. It also requires a lot of interdisciplinary expertise because you need both domain experts, you need experts in quantum algorithms, experts in compilation, etc. It's very error prone. When we work on reproducing the results from some papers, we often found errors in those papers. And furthermore, I really liked what Will Zhang was talking about a couple of years ago about resource estimation. I don't remember the exact algorithm they were working on. That was when he was leading the group at Goldman Sachs. But he basically mentioned that they had some resource estimates from the project that they got with basically pen and paper. And then when they used software from Microsoft to do the resource estimation more programmatically, after a couple of months, they got basically the same numbers for the resource estimates. And the reason was that on one hand, they have optimized a lot of pieces of their algorithm, but on the other hand, doing this programmatically uncovered that they have certain bugs or they made certain mistakes, which just made the resources much lower. So kind of the optimizations balance out all the errors they have done. And the last issue is that the results are often scary, because if you tackle a new application, which just no one ever had before, and you get your first resource estimate, like how long it will take to run it on a quantum computer, you often get numbers like tens of years, and some like obscene numbers of qubits that wouldn't fit on would like basically given in like billions or thousands of billions of qubits. So this is often, I would say, like a bit problematic. So the solution to that is creating tools that will allow to like accelerate the analysis of applications, drive the development of new algorithms, and at the same time reduce the resources required to do that. And here is a plot from another project that we did, where each of those dots was again months of work to figure out that something takes that many T gates and that many qubits. And what we would like to, the world we would like to be in is the world where we can actually populate, this whole plot with many, many different dots for many, many different applications, problems, materials, molecules, etc. And especially we can focus on those most promising applications for the near term kind of fault-tolerant quantum computers, like fault-tolerant quantum computers of like the first generations. And this is really not doable without software. So looking again at this picture, basically we want to change it so that all those stages that we can automate, because, well, to be honest, the problem definition is something that we will always have to do manually, can be taken from months or weeks into days, or in case of resource estimation, even minutes. And I have to say that I asked Sam Pallister, who is leading the whole kind of applications department at PsiQuantum, about how far away we are today from these numbers. And I was very glad to say that, like, he said that, well, actually those numbers look much more, we're pretty close to getting to these numbers, at least with our internal software. But also in the public domain, there has been a lot of great developments in the last couple of years that allowed us to get from here to here. So I will talk a little bit more about that in a couple of slides. So for the sake of time, I will get into resource estimation. But first, do we have any questions? Great.
We're good to go.
Okay, awesome. So I would say, even though the title of the talk was called Introduction to Resource Estimation, and I only now starting to really talk about resource estimation itself, I hope you don't mind this, because I really think it's very important to like motivate why we need resource estimation in the first place, and why this is a problem that people spend so much time kind of trying to, well, get better at, right? This is exactly because resource estimation is one part of kind of this pipeline here, which allows us to iterate more quickly on getting better applications, better algorithms. And obviously there are other parts that are very important as well, but, well, I focus on resource estimation, so that's what I will talk about. Okay, what is resource estimation? Quantum resource estimation, right? This is a process of establishing what resources are needed to run a particular algorithm on a, well, particular fault-tolerant quantum computer or a generic fault-tolerant quantum computer. I would say that there's a couple of caveats here, that resource estimation as a kind of a subfield of quantum computing is very new. I think, it's people have been started seriously doing resource estimation just a couple of years ago. We are this year at IEEE Quantum Week conference. We will be running the third workshop on resource estimation. And I think the only other workshop on resource estimation was one organized by Alexandru Paler like 1 year ago. So we are talking about like 4 years of having events. Yes. And the second thing is that terminology is not very well established, and different organizations will use different terms to describe the same things, or the same term to describe different things. It's sometimes slightly confusing or extremely confusing. Really nothing here is very well established. There are no guidelines, just like everyone is trying to get the best resource estimates they can. Fortunately, there is, I would say, quite a bit of dialogue in the community, and we are working on making sure that we can talk to each other. But just keep that in mind, that if something that I will be talking about doesn't map to what you already know? Well, it might be just because of these issues here. So I would say that when it comes to classifying the QREs, there's a couple of distinctions. So first, and I think most important one, is logical versus physical. So logical QREs refer to estimating the resources needed to run particular algorithm in terms of logical resources. So basically, this is kind of before doing any error correction. And in this case, the resources people most often use for logical ones are T-gates or Toffoli gates. Basically, with some caveats, but the T-gates and Toffoli gates can be used interchangeably in the ratio of 1 Toffoli gate is 4 T-gates. But I don't know, like some people use T, some people use Toffolis. And another one is logical qubits, which is, well, like logical qubits, right? So these are logical qubits. When we kind of get back to the pictures I've shown before, those like big squares, which are built out of, for example, like D squared physical qubits. And usually T-gates are a proxy for time, and qubits are a proxy for memory, right? Then when it comes to physical QREs, this is where things are like more interesting, I would say, because the metrics that people most often use are wall time. So given the assumptions about the hardware, the error correction protocols, and whatever other details your kind of hardware model has, how long it will take to run it. So that's one thing, it's time. Another thing is, well, physical qubits, but I've also seen people doing resource estimations for the energy consumption or particular cost, like cost of building the quantum computer. I've seen like people having actually like very detailed models of the hardware in terms of like physical hardware, how many dilution refrigerators you need to contain that many physical qubits, what are the interconnects between them, and etc., etc. So this can go like pretty detailed. Another distinction is between numeric and symbolic resource estimates. 99% of the time, people, maybe 95% of the time, people will deal with numeric resource estimates. So we have specific numbers. This will take 10 to the power of 9 T-gates, right? Like this is pretty specific number. But sometimes people work with symbolic expressions. And I would say that this often happens for the algorithm at like earlier stages. Sometimes people do, estimate things in terms of scaling and big O notations, and this is usually done symbolically. But also, I developed a library called Bartiq, and in Bartiq we build symbolic expressions which allow you to see like generate like programmatically, not with pen and paper, how much T-gates, qubits, whatever the particular algorithm will cost, and then with such expression you can actually analyze the scaling, get some more insights than just from looking at kind of arrays of numbers, right? Qualtran also provides some capabilities. Qualtran is a library developed by Google, also provides some capabilities for doing symbolics. And you can also classify them by level of detail. There's no kind of particularly strict categorization here, but as you will see in a couple of slides, like some of them are much more detailed than the others. Okay. how does the pipeline of generating those resource estimates usually looks like? So we start from the left with two things. One is problem instance, the other is algorithm. So what is problem instance? Problem instance is all the input data that you need in order to specify your problem. That's obviously depends on the domain. But for example, in chemistry, this might be, well, like all the regular chemistry stuff. So like number of spin orbitals, the precision up to which you want to get particular quantity. In optimization, this could be, well, a graph and the weights of the graph that describe your problem. The cost function, perhaps, things like that. When it comes to the algorithm, algorithm is separate from the problem instance, right? Problem is the problem you're trying to solve. Problem instance are specific numbers that you will use to define this particular instance of the problem. An algorithm is, well, just a recipe how to solve it. So, it can be quantum phase estimation with different block encodings, or maybe Shor's algorithm, or maybe QAOA, whatever your heart desires. Then usually once we have this information, we can do some domain-specific preprocessing, and this is kind of something I will keep intentionally vague because that depends a lot on a particular domain. If you ever work with quantum chemistry, Psi4, OpenFermion, they provide a lot of preprocessing tools for this. Then usually the next stage is to get a rough implementation of a logical circuit. And by rough, I mean the kind of first approximation. And only once we actually know something about this rough implementation, then we can get to the detailed implementation. Why, this is two separate stages? This is because going from rough to detailed can really take months. And often in many projects, what we want to do is we first try to get the rough implementation, get resource estimations out of this to see which variant of the algorithm we want to use seems most promising, and then implement only that and not all the algorithms that we are considering. Then we might sprinkle a bit of other specifications. So for example, specification of the quantum error correction and the architecture that we want to use, the details of the hardware, etc., etc. And that will give us some detailed implementation like the physical level. And from that, we can get physical QREs. So you actually, any questions for what I described?
How are we doing there? Any questions? I don't hear any, so.
Okay, great. Let's move forward. So what does a QRE looks like? There are just so many ways people express these. For example, here, this is just a dictionary. Like we in that particular project, we specified how many resources you need for particular block encoding, then for the whole algorithm, and then we did some numbers to calculate the physical QREs. If we click, I'm not sure if that will work. One moment. Do you see my browser or not?
I see your PowerPoint.
Okay, so one moment. I shared. Okay, do you see my browser now?
Yes.
Okay, so if we look at the Azure Resource Estimator from Microsoft, they have extremely detailed output for their resource estimates. So you can see that there are things like physical counts, logical qubits, T factories, But then physical counts is just a dictionary which contains kind of more details and more details. So logical depth, number of t-factories, number of t-factories runs. As you can see, there is just like so many details that you can get out of QREs, right? If we compare, you can even visualize it nice like that. But basically, I'm showing this just to show that there is a lot of different ways to kind of like a lot of details. Depending on your QRE machinery, you might get to really nitty-gritties and have like simple dictionaries like that or extremely nested dictionaries. Another way to express them is using call graphs like that. So this is extremely useful representation because it allows you to see which part of the algorithm are kind of using most resources of particular type. So this is generated by like one of our tools, and it's taken from some paper. And this is extremely useful because usually, rather than something like that, this allows you to see how much resources each subroutine takes and which is the thing that you should optimize most. But then, if you are comparing different applications, you can take QREs might look something like that, right? Where you have a couple of different assumptions about the hardware, which corresponds to different types of pointers, and then you can show what applications fall into which region. This is again taken from like some Microsoft paper, but this is also the plot that we've already seen with researches for different applications. And on the other hand, here for some of the applications that are, I would say, that like earlier stage of development, and this is mostly differential equations, I would say that in general, the cryptography and kind of chemistry are the most developed ones. But some like things like differential equations are still, there is still like a lot of research to be done. So in this case, we can see those symbolic expressions describing what's the scaling of particular algorithm. Okay, so why getting high quality QREs is important. I already mentioned that this is important because it allows us to iterate quickly on like getting them fast allows us to iterate on the algorithm, finding the bottlenecks and like optimizing the costs, like the resources needed to run particular algorithms to kind of solve particular application. So that's part of that. Another thing is hardware design. So imagine a scenario where you can build a quantum computer. You are you're responsible for building it. And from what I heard from kind of designing a quantum computer, that you can do basically anything. Like there are so many trade-offs you can make on so many different levels that hardware people building hardware, they need some guidelines towards what particular hardware they should build. Because imagine a scenario where they decide, okay, we'll build 100 qubit fault-tolerant quantum computer with kind of this error rate. And they build that. And everyone is super happy. But then the people working on the applications say, we have this really great application that solves, I don't know, like high temperature superconductors. And it requires 107 qubits. And then the hardware people say, well, if you told us that you will need 107 qubits, then we'll build you a 107 qubits computer, but we build you 100 qubits computer because we didn't have good specs, right? We didn't know which parameters should we trade off between like other parameters. And suddenly you might end up with the great machine that costed $1 billion that actually doesn't solve a useful problem, even though it could if you just change the specs a little bit. So QREs are really important for not just algorithm design, but also hardware design. It's definitely also, it's definitely great tool for decision making to see, well, just like what's worth our time, and both at the level of particular algorithm, where on plots like this you can just see, okay, we really need to, I don't know, optimize this particular subroutine because it's the one that's taking most of our time. Also at the level of applications, it allows you to see which applications are closer to reality, which are further away. So which should we prioritize? And yeah, as I said, like rapid prototyping of algorithm, it's really hard to design new algorithms if you kind of don't have that feedback loop. So it's important to remember that having QREs is just a part of the puzzle, because we need many other things, as I mentioned in the first part. So first we need to actually have those algorithms that are doing something useful. We need to know what are some applications which are promising. And also compilation of in this whole process is also crucial, as it allows you to get like huge optimizations and huge cost savings. So that's QRE software is really just like one part of this whole big puzzle. Okay, so what kind of software do we have when it comes to QRE available today? So let's say you got interested by this talk, you want to play with something. What is out there? So I would say that there is definitely Azure QRE tool from Microsoft. I think it's the most probably most polished, most user friendly in a sense. I mean, it's like very well documented. There is a lot of examples, so it's definitely a decent tool. Another library is Qualtran. It's developed by Google. I also highly recommend checking it out. It's developing very rapidly, and they have that like really amazing job at Google developing it. PyLector, this is a library developed by MIT Lincoln Labs, and it contains a lot of utility tools that are centered around QRE. I don't remember exactly what they, what's there right now, but they have a lot of different algorithm implementations, some examples for like different applications, some compilation methods. So there is a bunch of example notebooks there. You can check them out. This is, I would say like maybe less comprehensive than, for example, Qualtran, but extremely useful library and worth checking out. And last but not least, there is QREF and Bartiq, which are the software packages that I personally work on. QREF is quantum resource estimation format, so it's a particular format that we use to store and exchange our QREs and algorithms, while Bartiq is I would say like compilation engine for symbolic resource estimation. So it can produce symbolic resource estimates and also has a bunch of tools that allow to analyze it. Okay, so wrapping it up, I would say that NISQ and FTQC mindset are very different, and whenever if you are focusing on NISQ and variational algorithms, and you would like to understand the fault-tolerant world, then keep that in mind. Like they're so different on like so many different levels that it's sometimes confusing, and it definitely was confusing for me. There is plenty of work that we need to do as a community of fault-tolerant application and algorithm developers. Oh my God, I just like don't know where to start on so many different fronts. We need better tooling for QREs. We need better compilation. We need some libraries of algorithms, formats to define and exchange those algorithms, etc. That's really there has been like a lot of development done in the last couple of years, but there is still a lot ahead of us. And also QRE is a tool that can help us with a lot of these, right? Finding new applications, speeding up the feedback loop, and guiding the development of new algorithms and also the development of hardware. Okay, so here I have a couple of sources for learning more about the topic. So first, I have a blog called Musty Thoughts. I have written a little bit about QRE there, but I also have like the resources section with a lot of potentially useful materials. There is a workshop focused on QRE that I'm co-organizing at IEEE Quantum Week, which is happening in Albuquerque in a couple of weeks. There is also a workshop in Helsinki that's happening, I think, right after Quantum Week, so probably like second week of September. There is this paper. I think this paper is a great introduction to QRE, utilizing QREs for application development, so feel free to check it out. And also, it seems to me that very good way to learn is also to just review the software packages that I have mentioned. So Azure, Quantum, Qualtran, PyLector, and Bartiq. You will find some interesting perspectives in each of them. And about like some other topics that I have mentioned, Daniel Litinsky, Game of Surface Codes. I would say this is the best introduction to some of the fault-tolerant architecture and kind of error correction compilation that there is. The paper is from 2019, I think, so a lot happened in the field since, but Daniel has great visual style of explaining very complicated concepts, so I recommend that. Artur Pesa has written a great couple of blog posts on error correction, which is also a great intro. We have some resources on the PsiQuantum's website, so that as well. And as always, I think the best way is to reach out to people in the field. So if you want to reach out to me, I'm pretty easy to find. Here's my email. If you don't remember that, just find me online and I will be happy to help. And mostly unrelated to what I was saying for 90% of the talk, but recently with my friend Conrad, we have started a newsletter where we write that's targeted at software developers working quantum and researchers writing software for quantum, where we each week like share some knowledge about writing software for research in quantum computing. So it would be great if you could check it out as well. And I think that's it. And oh my God, I'm so sorry. I don't have a thank you slide. I forgot about it. Thank you very much for listening. I usually try to remember about having it. I appreciate your time, and I think this is good time for any questions.
Your verbal thank you is just fine.
Yes.
Thank you.
Questions. Unmute yourself and ask. There's a question in the chat. What would you say is the most important problem in quantum computing, if there is such a thing?
Oh my, I think there is just so many so many most important problems. depending on the particular place where you look. Definitely different hardware platforms have their own problems. I think error correction protocols are also still not there. But I will answer that from my perspective because I'm sitting, on a pretty high level of the stack. And in my opinion, the most important problem is finding like really good applications for a quantum computer and making sure we have it specified to the level where we can actually run it, and just minimizing the resources needed to run this. I think one of the first, I would say it seems that one of the first applications of for quantum computers will be running solving Fermi-Hubbard model, which is maybe not very commercial application, but it's definitely interesting scientifically. If we could spend just improve the resources needed to run it by an order of magnitude more, then that will be great because it will take that much less time to run it, or it will fit on first generation quantum computers. So that seems to me that this is looking for great killer applications is a very big and unsolved problem. One more resource that I have forgot to include is if you go on DARPA's website and you look at quantum benchmarking program, and this is different from QBI, Quantum Benchmarking Initiative, which is a program that came after that. I will find a link and actually post it in the Slack in a moment. They have a list of papers that came out of quantum benchmarking program with some great ideas for applications for quantum computing. So that's interesting resource to learn more.
I have a question. I have another question. Hi, this is Messiah Moody.
Hello.
Isn't it difficult developing quantum algorithm?
Joe, are you in the middle of something?
I'm sorry?
I just got back in, and then it was raining.
Sorry. Oh, thank you.
Go ahead.
Isn't it difficult developing the quantum algorithms or software when the hardware is still evolving and there are major technical impasses or blocks or obstacles to overcome on the hardware end? Traditionally doesn't software find an application that makes use of the hardware? So wouldn't it necessarily lag behind what the hardware capabilities?
So I would say, and this is linked to the paper in the chat. Yes and no. So the reason why no is if you have a well-defined layers of abstraction, then that allows you to independently work on different problems, and you don't need to concern yourself about the hardware. Like similarly as in classical, let's say network when I don't know if you know OSI model for kind of classical networks. So basically this is a simple layered model where at the very bottom you have the hardware and literally how does a cable for connecting to computers look like, and some higher levels you have network protocols. So how do you route, routing, etc. These two problems are just separate problems. You can work on one without both having any knowledge about the other one.
No.
And I would say that this is something that we are slowly developing. I posted a link to the work we did with some other people on the topic. And so in that sense, if we had well-developed layers of abstraction, then what you're saying wouldn't be that much of concern. Unfortunately, we don't have well-developed layers of abstraction at the moment. surely working on application versus working on some like optical switches are just, they don't have that much in common. But I dread a moment when people from our architecture team will come to us and say, oh, actually you figured out how to make T-gates so much less expensive that suddenly like you have to rewrite your whole QRE stack because now the assumptions that go in are so different. It didn't happen yet, but this is something that to some extent is that could be problematic. At the same time, it just requires a lot of dialogue between different groups, and also I would say there is a lot of problems. There's actually a lot of problems that are orthogonal to each other, and there are also other problems which at least from my experience, they look scary at first, but actually once there is some switch in the assumptions, it turns out that accounting for that doesn't always mean you have to rewrite everything from scratch. So it's like, though, yeah, it's not easy, that's for sure.
And we're far away from the point where we can use quantum computer to write quantum software.
I hope never. I hope never. I mean,
Thank
there is an.
So I have a question. It sounds like you've built some frameworks. And did I understand that they take as input like a mathematical expression?
That's the output.
Pardon?
That's the output.
Well, I mean the original mathematical problem that you're trying to solve with a quantum computer, is that one of the inputs?
I would say, okay.
And if that's the case, is the framework have tools to do that translation or assist with that translation?
I would say no. Usually what happens is that going from like the domain problem to some mathematical expression is something that just like takes a lot of manual work of experts. So that's kind of one part which is very hard to automate. And I would say that people have been trying that for a long time in, let's say, classical optimization, for example. And I don't think we have ever really succeeded in kind of automating that part, right? Because if you have an optimization problem, you can define traveling salesman problem with a graph, right? And you can say, hey, solve traveling salesman on this graph. But then it turns out that in practice, there is a lot of extra caveats. You almost never want to solve a vanilla traveling salesman. You need to add certain like time windows, for example, or it's like distributed or something. And then the frameworks that allow you to go from very simple representation of the problem to like some solution or algorithm usually just are fairly limited. And I would say that's even for like kind of classical problems. So there is always a lot of work that you need to spend on taking the real world problem and just like translating it to the format that your particular software package can handle. Which is something that like happens a lot in like operational research and optimization, I think. Right. So
as input, you need some sort of high level description or high level quantum algorithmic description to feed into your frameworks to get an estimate.
So usually what is an input to the QRE kind of software packages is quantum algorithm or program written in some
an actual circuit, a quantum circuit.
Sometimes it's a circuit. Okay. I would say that I have written the whole other piece on why I don't think circuits are a good representation. So usually So for example, in Qualtran or in some of our internal software or even external like Bartiq, the input is really not a circuit, but it's more kind of some other representation. So this is in case of Bartiq, it's a routine with like a hierarchical graph. So you have a routine which has subroutines, which has their own subroutines, etc., like
Mm.
many layers deep. And at some point, some of these could be written as circuits or written as just like gates, and you can construct a circuit out of that. But usually, like one of my big issues with the kind of current state of community is that we need to go beyond circuits and just like have better representation for those quantum programs and algorithms.
Yeah, and you kind of hinted at possible issues with like big block unitaries. Lots of people put them in their papers and they put them in their research, and then there's a little caveat at the bottom. Oh, we haven't actually coded this unitary.
Yeah.
Do you have a way to deal with that? Do you just insert a placeholder? How does that work?
I would say, okay, software-wise, for example, in Bartiq, you can just say, this is the level where I stop and I don't want to decompose it anymore. Here is an expression that defines how many T-gates it needs to run. And I believe the authors of that paper that they provided me a correct expression. So that's one way to go about it. Another way is, one way is to believe someone that they did good job at kind of decomposing the problem enough and just estimating what the expression is. Another is painstakingly spend months decomposing it yourself until you eventually have some executable circuit. And I would say that the issue here is, on one hand, that you could use an automated process to solve this sometimes, right? Like we have software that takes arbitrary unitary and gives you a circuit for that. The problem with that is that right now we are not at the stage where I think doing that for really big subroutines is efficient. And usually you would like to use an kind of domain expert in compilation or like quantum like arithmetic to just construct this for you manually. And that usually ends up with much more efficient circuits.
Okay.
Okay,
I have two more questions, and then I'll let the crowd talk.
I just want to. I want to do a Robin here. We have a hand raised, and then Ron, maybe we'll get back to you in a sec.
Okay.
Yeah, and Bill Slater, I saw him waving his hands furiously at the camera. I don't know if that's because he's trying to get our attention or not. Or Bill, are you here?
He was on mute.
All right.
Sure.
Itamar, do you want to ask your question? Then we'll get back to Ron.
Yeah, I wonder, this is a bit of theoretical approach. Are you aware of anybody who tries to translate some of your challenges to pure mathematical problems? Because there is treasure of tricks and key toolkits in mathematics that may be unearthed treasures that can solve the challenges that you are raising here, because you're approaching things from very practical approach. Even Ron's question was practical in my mind, but pulling to the theoretical side, it could be that, even some open mathematical problems may map, or you can map your challenges to those open mathematical problems and then get some elegant overview or killer app to some of the challenges?
So I would say that okay, let's put it this way. I'm an engineer, not a researcher, and I'm usually focusing on kind of solving some engineering problems.
Sure.
So I'm not let's say I'm not aware of a lot of the developments in the field. When it comes to kind of more theoretical approaches, I think that from my experience when working with applications themselves, then it just requires a lot of manual work and manual effort and like domain expertise and people talking to each other to kind of come to something. But I definitely have seen some interesting like solving some other issues in the field with, I would say, more theoretical approach. And definitely some of the compilation problems, I think people have spent some time reformulating them in a kind of more elegant kind of mathematical language, which really enabled a lot of progress. I mean, I'm not that familiar with that, but it seems to me that ZX calculus can be an example of that, where really a lot of the compilation is there has been like a lot of effort in that went into ZX calculus, and it really enabled a lot of very efficient compilation techniques.
Sorry,
Another
calculus?
ZX calculus.
ZX. Okay,
Calculus. Yeah.
that's
So
okay.
I think this could be an example of that. And another one, there is, the whole kind of topic of verification of algorithms and whether they actually do what you want them to do. And obviously you can simulate some smaller algorithms and just verify with simulation whether what you run on the actual device gives you the same results. But I would say that some people are working on formal verification techniques, and this is also something like I don't know exactly how it looks like right now, but it is an interesting direction that I think falls into what you described, where just having some very solid mathematical foundations that can solve some problems.
Thank you.
Tom, you have a question? We can't hear you.
Yeah. No, can you hear me now?
Yes, indeed.
Okay. Well, first, Michał, thanks for the very nice presentation. I learned a lot being kind of new to this field. So I have two questions. I don't know if you could go back to the slide where you have this pipeline showing the. Is Michał still here?
Yeah.
Okay. To this slide where you have this pipe. Yeah, this one exactly. So you did mention that within your team or with your colleagues you were able to reduce the steps, which took months to like days.
Yeah.
And I was just curious, like, how did you do this? Like, what's your magical sauce? Because from the way it's formulated, and I think someone has also like pointed it out in the comments, I think, could this not be a problem which would be very approachable if you like formulate it as a machine learning problem? Like you get some kind of input, and well, I don't know what I'm talking about, so I'm just speculating.
Yeah, I know. I would say so.
But how did you solve it in this case, and could that be a way to approach it?
So I would say that there is let's take a look at this. Like there's a couple of items. So when it comes to algorithm selection, what you want to have is like access to some library of subroutines. So rather than I'm actually this is something that helps with both of these. So when you see a black box in a paper and they say, oh, like here is let's say an other, right? And They just say, here is register A, register B, and then voila, register C contains the result of your addition. I mean, this is something that's like reasonable to say in a paper. But then when you want to actually implement it in code, then you need to figure out how to perform this addition. And obviously, addition is a silly example. People already did that many times. But like someone had to do that for the first time, right? So once you implement those subroutines, then you can reuse them over and over and over, and you can compose them into bigger subroutines. So one part is building this library of subroutines and then composing more complicated out of the simpler building blocks. And over time, this just accumulates, right? So this is one part of that. Another is, I would say, the interoperability. This is a huge problem. I would say it's not solved on the level of the community, because a lot of different software packages use kind of different standards, different formats, but it's getting better. And this is also something where if you have good interoperability between different pieces of software, and let's be honest, like each of these is usually, like each of these problems is solved by different piece of software, then that reduces a lot of the friction and just speeds up the process. If you have to, going from someone selecting an algorithm and doing that kind of manually, pen and paper, to someone else having a library that is kind of writes some of those kind of subroutines, and then someone else taking this and like doing compilation. If each of the steps requires some transpilation between formats, etc., that's annoying and waste of time. At the same time, it's not easy to develop a unified framework from the start, because different groups have different needs here, right? Like you need different representation for like low-level compilation and different from describing high-level algorithm. So high-level languages and abstractions is also something that we've been developing and like improving kind of syntax for being able to express certain things better. And then, well, automated compilation tools similarly, right? This is something where you sometimes need to, at first you take a particular subroutine and you just like look at it very hard for a couple of days, and then you notice that there are certain symmetries, certain tricks that you can use to make it more efficient. And then over time, you see patterns and you start seeing that, oh, actually, I can encode this particular trick into like some small algorithm that allow me to like a compilation pass, right? Like I can always simplify this type of gates into like this other type of gates, and it usually makes it more resource efficient. So over time, that just allows you to do it more efficiently and then like automatically. So I'm not sure if this is satisfactory answer. It's just like a lot of work and like people just improving the tools over time, and accumulating that knowledge and expertise just allows you to really get further and further.
Yeah, no, I was just saying, because if this could be a bit similar to what I think it was Itamar was saying, like if you could formulate this into some kind of machine learning program with some, framework with some kind of inputs and known outputs, then you could probably train a system to do this. Maybe not better than a human, but maybe to scale it up for the parts which are not so complicated.
I will say I have seen people proposing different machine learning models for different parts of that. I would say compilation is probably the one that's most ripe for it, because you have like, this is the input, this is the output, and just like find a kind of better way to kind of express that. It's a more kind of data driven, let's say, potentially approach. And I personally, I don't know how widely used it is in practice. I know people have written a lot of packages using machine learning in compilation, but I just know whether other people are using those packages or whether they were just like interesting research projects. I think they do, but I'm not exactly sure. So in this case, yes. In the other, I don't really think we have, even when it comes to like the algorithms design or construction, I don't think we have enough data to really train any models. There is just a handful of algorithms, a handful of subroutines. Um, I would show you mine, like ours, but I don't have that. So I will show what's in Qualtran. So for example, Qualtran has those blocks, and these are different, like for example, like arithmetic routines. Um, each For each of them, you have 3 files. So there's like notebook, Python, and test. So you can divide the number of files by 3. But basically, this is kind of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 files, maybe 11, right? With different arithmetic routines. That's not a lot, like maybe there is like each subroutine in Qualtran is called block. I guess maybe there's like 100, maybe 200 of them. I don't know, blocks library. Uh, there's that many of them. By the way, actually, some of them are like very similar, like comparators. You have, like greater than and less than is, is basically the same thing. Like just the sign is different. So, here, let's say you have some of them are just gates, right? Like, so this is how many subroutines you have defined. I would say in Qualtran, they are not all are defined in in a very detailed way. So this is the amount of the input data that we are talking about potentially to those machine learning models. I don't think this is enough to really get something really good, significant.
I've been feeling guilty for the last 20 minutes about putting Ron off. Ron, you have a couple questions. I assume that it's getting close to midnight in Poland. Are you still awake and okay?
Oh yeah, sure. I always love
Okay.
All right,
discussions.
okay.
All right. My first question is very quick. Will you be able to share your slide deck with me or Barry so we can post it on the meetup group? Either a copy or a link. Yeah.
I need to ask my marketing people because they
Okay.
are. I mean, I really hope it's not a problem because come on, it's like already shared it with you. You can just like have screenshot it, but I need to ask them so not to upset anyone. Like how it is. Sorry, but
All right.
yeah,
So,
I will make myself note to make sure to ask
We'll
them
keep
tomorrow.
in touch.
Yeah.
so my last question will be, is the work that you're doing, do you think is going to be extensible to some of the multi-modes of a quantum, a neutral atom quantum machine, which has the ability to operate in different modes, and or a quantum annealer?
So for neutral atom, okay, any work done on the logical level of those circuits is basically logical. When you're operating at the logical level, then it has absolutely makes no assumptions about the hardware that is below. So it can be used on any hardware supporting fault-tolerant quantum computing. So whether that's neutral atoms, superconducting qubits, ion traps, or photonics like what we do, it doesn't matter. So in that part for sure. Annealing is kind of a very different paradigm. So I would say any of what I'm working on would relate to annealing, really. Maybe you could do some magic to kind of link that, but it's very non-trivial. So I don't really think so.
Okay, great. Thanks.
I also wanted to just like address one thing that I see in the chat from Sean regarding agentic AI. So I have been playing with Copilot and recently in VS Code, and oh my God, it's like not working very well on writing most of the code. And I mean, it's not terrible. It's helping with certain tasks, like documentation or writing test cases for sure. But it really gets lost in the details. Like the AI is not here yet to deal with quantum computing, at least not from my experience. There is just like too much kind of tacit domain knowledge that you need to have in order to even kind of verify whether it's done a good job. Most of the time, if I haven't done the thought process myself, it will take me the same amount of time that if I were to just verify whether the AI did that. So it's like not much of the kind of time improvement. At least like from my limited experience. So
I agree. It's good for making a draft. I'm sorry, Sean, go ahead.
I was thank you for answering my question there, but I was actually talking about the general trend when AI, for example, I don't know if those models already exist, but given enough, I would just say maybe sometime down the road, a lot of that work can be handled by an AI system, not the consumer version that you and I are using right now, but possibly because there's a big push to basically use AI for quantum as well as quantum for AI. That's where some of the immediate convergence is taking place in the industry. So I was referring to a sort of macro development rather than something like I said, you and I can use.
Yeah. So I would say when the argument for using AI for quantum, I think, is the same as the argument of using AI for anything that you can do mostly with your computer, which is at some point the kind of the level of intelligence of AI will be so high that it will be able to do whatever we are doing. So yeah, I think, but there's nothing special about quantum. It's, like 90% of my job is software engineering. So that's kind of one part of that. On the other hand, I'm extremely skeptical about using quantum for AI in any way, or like machine learning, for various reasons. But I haven't seen anything really convince any apart. Okay, while at Zapata, there was some interesting research for using quantum for generative AI. But it was kind of extremely early stage, and I'm not sure whether it's actually scalable. So about that, I'm very much skeptical.
Okay. Wow. And it is, yes, 1 minute to midnight where you are. So we thank you very much. Fantastic talk. We really
Thank you.
appreciate it.
Glad you liked it. Also, like if anyone, I will be at the conference. If anyone goes to the conference, then like please catch me there. And yeah, if I will be traveling to Chicago at any point, I would love to kind of meet with some of you guys. So
Here I am on the East Coast near New York City. So if you come down here, everybody join us in September. Let me take a look. It's 18th. And we're going to be talking about, training neural networks on quantum computers. How about that? Speak of the devil. All right.
Right.
September 18th. Look at Meetup to check it out and absolutely register. Okay. Good afternoon, good night, good evening, good morning. Everybody have a good one. We'll see you next month.
All
Take
right.
care.
Thank you.
Thank you very much.
Thank you, Barry. See you next
Very
month.
right.
Bye.
Thanks
Hey,
a lot. You guys are the best.